so I can explain some bits to you. So can you guys see my screen? You can see this?
Yeah.
Perfect.
Yes,
Okay.
yes, yes.
Nice. So fractional distillation, it's a really, really important concept in organic chemistry because it really was the technology that allowed us to start extracting some of the chemicals that we've been learning about. So those homologous series that we've been looking at, like the alkanes and the alkenes, all of them come from fractional distillation, basically. So the aims today, guys, is to look at fractional distillation and then look at some of the fractions or the things that we get from fractional distillation, okay? So we should have learnt a little bit about this a long, long time ago at the very beginning of year 10 when we were looking at separating techniques. So can you guys remember some of the common separating techniques that we used?
Filtration.
Yep, filtration, thank you, Josiah. Anything else?
Chromatography.
Nice, Gabriel. Yeah, chromatography is another one. Any others?
Simple distillation and
Distillation.
Yep, distillation is one of them, or, you know, simple distillation.
What about crystallization?
Crystallization, yes, we can use recrystallization is another separating technique. And probably the most simple one, which nobody mentioned, which is just filtration, right? You can simply filter them out.
I mentioned.
You mentioned? I'm sorry, Josiah, I take it back. So, fractional distillation is just another separating technique, really. It's all it is. And it works when you have liquids which have different boiling points. So, imagine you had a solution, and in that solution you had some treacle at the bottom here, and then you had some honey, and then you had some, I don't know, oil, and you had some water. So you have a big mixture of different liquids. And the nice thing is all those liquids will boil at a different temperature. That's basically what you need. What we do is we heat all of that mixture of liquids up, and the liquids which have the lowest boiling points will boil, become a gas, and then we can separate them off as either a gas, or if we condense them again, we could get them back to a liquid. Liquids with high boiling points, the ones that need to get really hot before they become a gas, will stay liquid for a long time. And so that way we can keep them at the bottom of the container. So let me give you some numbers just to give you guys some ideas what I'm talking about there. Imagine up the top here we had water, which we know boils at 100 degrees centigrade. Maybe down here we had some oil, which boils at 200 degrees centigrade. And then right at the bottom here we had some treacle. Treacle. No idea how to spell treacle. Probably not like that. It's probably a C. C, something like that. And that maybe boils at maybe 400 degrees centigrade, let's say. Yeah? If I was to heat this mixture of liquids together, the water would boil much faster than the oil would, and the oil would then boil faster than the treacle. So if I was to heat the whole solution to 120, let's say 106 degrees centigrade, the top section here, it would boil off as a gas, leaving behind the bottom sections, this part. It would all be left behind. So that way what I've done is I've managed to separate my water from my oil and my treacle, haven't I? If I then heated the solution, kept heating it, and I got it to 206 degrees centigrade, then the oil would now turn into a gas, and I could collect that off separately, and what would be left behind would be just the treacle layer, wouldn't it? I'd be left with just this part here. So can you see how by using the boiling points I can separate liquids?
Yeah.
Yes.
Yesterday.
Nice. So fractional distillation is generally not used on water, oil and treacle. It's actually much more commonly used on the crude oil that we dig from out the ground, which we learnt about in our previous lesson. And that's because crude oil is made of a huge mixture of different chemicals, and they all have a completely different boiling point from each other. So let's have a look. Crude oil, we should know by now, is it contains hydrocarbons, and basically there is no use for crude oil by itself. Nobody digs it out the ground and goes, right, I'm going to use this in my car. We have to purify it first, or refine it, to use the proper word. Refinement is done in something called an oil refinery. So this is a picture of an oil refinery, which is an enormous building made up of lots and lots of towers, and those towers are where fractional distillation takes place. So let's have a look at some fractions. How does it work?
Refinery? How do you spell refinery?
Refinery, sorry. Refinery. You can see it here. It's written. It's there.
Alright, I'm done.
You're done?
Oh.
Okay, so how do we do it? If we were to look at one of those towers in a lot more detail and like blow it up so we could see inside, what we'd see is we'd see this kind of structure. Basically, a load of layers of these upside down that look kind of like bowls upside down. And then we'd see the solutions moving, the mixtures moving through them. So, number one, the very bottom, this whole tower, as it says here, is called a fractionating column. So, we call it a fractionating column because it makes fractions of stuff. And so what we do is we take, right at the bottom, we take crude oil, which we've dug out of the ground, and we pump it in. But the crude oil is not cold, it's already at a very high temperature. It's at 370 degrees centigrade. So we heat the oil up really, really hot, and then we pump it in. At the bottom, the temperature is very high, but at the top, by the time that these gases have made it to the top, the temperature is a lot lower. It could only be maybe 50 degrees centigrade or something like that. So by here, the temperature is very hot, and by here it's very, very low. So what we have is we have this range of temperatures, and as we move upwards, it cools down. And this is important, the fact that there is this range of different temperatures, because different parts of the crude oil, or different fractions of the crude oil, will boil at a different temperature. So generally, what we can say is that heavy fractions, or molecules that have lots of carbons, so long chains like decane and things like that, will have high boiling points, and that means that they will condense near the bottom of our fractionating column. So long carbon chains will condense into a liquid at this point.
Mm-hmm.
And what it also means is that short carbon chains will either condense at this point or they'll remain a gas. And that's because the temperature is still above their boiling point. Can anyone name an organic chemical which has a very low boiling point?
Methane?
Yes.
Or no?
Yeah, methane, Gabriel, right?
Okay.
So methane, or methane as the Americans say, will always be a gas because its boiling point is much lower than the boiling temperature that we have at the top of this column. In fact, methane is, I think it's minus 170 degrees centigrade is the boiling point of methane. So it would be very, very cold before it was actually boiling. So this one just says lighter fractions have low boiling points and condense further at the top of the column. Do you guys understand that? So just by using the boiling points, we can separate these liquids out. Things to bear in mind, these caps, you see these little parts here that look like bowls that are upside down? What they do is they're quite cold, and as these hot gases rise and touch them, they actually condense into liquid form, and then the solution comes out as a liquid. So basically all but the very top are going to be liquids as the solutions come out. The very top is going to be a gas because the temperatures are so high that they still will never condense. So every single one of these tubes coming out will be a liquid except for the top one, which will be the gases. Okay, well, that looks crazy. Let's go back. What's going on? Why is this doing this? Okay, so it should work. Can I click these buttons? No, excuse me guys, just while I get rid of this. Discard. Let's try that again. Okay, we'll do it here. Perfect. So, let's see this in action, because you can see it animated, it's probably easier. So stage 1, crude oil is going to be heated in a furnace until it's 370 degrees centigrade. Then what we do is we take that crude oil and we pump it into our fractionating column, and it basically evaporates because it's so hot that all of the gases pretty much evaporate. Those warm gases start to rise up, and either they condense on these plates that are here, this bit here, they either condense, or the gas continues to rise upwards. So gases that don't condense because their boiling point is still too high will continue to move upwards until we reach the very, very top. Excuse me. Anything that's not condensed by the time it's reached the top will remain a gas. It will never condense because the boiling point will be the temperature will be too hot. At this point now, we've separated our chemicals into different fractions of crude oil. And we give those fractions special names. And you guys need to know what the names are and also what we use them for. And so you might want to take some notes on this part.
Oh no.
I'll go nice
Can we just take a screenshot? Hold on.
You can, but I've also linked the PowerPoint for you, Gabriel, so you can watch it back at your own leisure.
Okay.
No, I pressed the thing. This is a screenshot.
The other thing that I'm doing for you today, guys, which I haven't done before, is I'm actually recording what I'm doing. So I'm recording my screen, and then I'll just link the video back to your OneNote, so you can watch it back and you'll be able to hear me talking through it as well.
Wait, I think Aiden's lost. She's asking me where's the chemistry class.
Okay, can you tell him to join the Hangout, Gabriel?
Okay.
Which he can find from Google Classroom. Okay, so let's start at the top. So the first fraction that you need to know about is gas. So the gas section, the ones that never become a liquid, they contain 1 to 4 carbon atoms long. So the molecules are going to be things like methane, ethane, propane, and butane. And we give these guys a special name which is called LPG, or liquid petroleum gas. Does anyone... That'll be Aiden then, give me a sec. Because he doesn't follow instructions. Where is he?
Hi, Robert. Who's Robert? Who's Robin?
Robin's my name, Josiah.
I think it's your first name, right?
It's my first name. Hi Aiden, thanks for joining. Okay, so, sorry guys, let's go back to where we were. Just a slide. So LPG, liquid petroleum gases. These are the chemicals that stay liquid all the way through. Right the way through. They will never become, stay gas. They will never become a liquid by the time they boil. Does anyone know what we use LPG for?
We burn it.
We do burn it, yep. So we heat our houses with it and things like that. If you've got if you live in a cold country, you might have a boiler and this will use gas. Or if you heat your water with a boiler at home for your shower, you might have a gas boiler which will be burning LPG. Taxis in Hong Kong as well. Some of them run on gas instead of petrol, and they actually run on LPG as well because it tends to be cheaper. And it's more efficient. It's cheaper for them to run their taxis on gas than it is on petrol. Okay, next one, gasoline. Gasoline, or as you guys might know it, petrol, contains 5 to 10 carbon length atoms. So this is everything from propane, all the way through to decane, which is where you guys have learnt up to with your carbon naming. This is also known as petrol, so this is the main fuel source that we get from crude oil. So anything you put in an engine, like diesel or petrol, comes from here. Any questions? No. Okay.
No.
Does anyone know what naphtha is used for? The next one.
No.
No.
Oh,
Okay.
I didn't turn on my microphone. Sorry.
That's okay.
Lost it.
So,
Yeah.
naphtha, guys. Naphtha is going to be 5 to 9 carbon atoms, so there's a bit of an overlap here. Naphtha is basically used to make plastic, but it's also used to make many other important chemicals. And it's also used to make drugs. So pharmaceutical drugs, not illegal drugs, for that next person who's going to ask a question, is made from naphtha. And a lot of the drugs that we use that are kind of good for pain relief or anesthetics, which are what they give you in a hospital to put you unconscious, a lot of this comes from fractional distillation of crude oil.
Wait, so I can make tranquilizer darts with it?
Tranquilized darts, no, but you can make a gas that you can breathe and it will put people to sleep. That will come from crude oil. Gabriel, yes.
Okay.
Okay.
Lost.
Okay, next one. Kerosene. Kerosene, which is in English known as paraffin. This is used mostly for jet engines. This is the fuel that aeroplanes burn when they fly. And so are really important for transportation. If we didn't have it, we wouldn't be able to make jet engines work. Kerosene.
So what color is it?
Oh,
What color is it? Most
Yeah.
of these are mostly transparent, but they can be slightly yellowy tinted. As you can see from the colors here, Aidan, the further down we go in this column, the darker the colors get. So they go from kind of clear to yellowy, and then eventually brown, and then eventually black.
What about the cost?
Car?
No, I mean the cost. Like, is it expensive or like?
Oh, that's a really good question. So in terms of cost, normally the fractions from the top are more expensive, and as we go further down, they get cheaper and cheaper.
Oh, okay.
The reason for that, Aidan, is because you make less when you do this process of the top fractions, and you make a lot more of the bottom ones. So these ones are much more common, and these ones are rarer in crude oil. And so these ones tend to be better, and these ones are worse generally.
Oh, okay.
Okay, diesel oil. So diesel oil, as the name kind of sounds, this is used for heating. It's not really got very many uses, diesel oil. It's used in some big lorries and ships use it as well to burn, but it burns quite uncleanly. It doesn't give out a lot of power. It's not the greatest fuel source. It gives off a lot of pollution when we burn it as well.
Gas oil.
Yeah, sometimes I've never heard it called gas oil though. Diesel oil is a much more common name for it. Okay, and then the final three are lubricating oil. So lubricating oil is used, as the name sounds, for lubricating things. So if you have mechanical engineering and you want to make sure it turns smoothly, then you might put lubrication oil in it. Or if you ever ride a push bike and you know the chain can get quite dry, so we put lubricating oil on those sorts of things. It's a very thick oil, quite viscous.
wait, is it dense?
It is very dense, yes. As we're moving down, Gabriel, the carbon chains...
Yeah, that's why I'm asking.
Yep, they're getting longer, right? So if they're getting longer, therefore they weigh more, and so the density will be increasing.
Uh-huh.
Okay, and then the last two, fuel oils. So fuel oils, 20 to 50 carbons now. We're getting quite long carbon chains here at this point.
Wait, what other uses? So
Of-
like,
Just for lubricating machinery?
so make things smoother.
Yes.
Move smoother.
Yes. It reduces friction, to be precise.
What's the boiling point of diesel oil?
Diesel oil, let's have a look. 260 to 340. Guys, you will never be asked for the boiling points of these chemicals, though, don't worry.
Do I have to write it down?
No.
Wait, do we have this PowerPoint?
Yes.
No.
Oh, okay.
You can open this PowerPoint. It's in your OneNote.
Oh, okay.
And also, Aidan, like I've said to everyone, I'm actually recording my screen at the moment. So what I'll do is I'll just put the video once it's finished. Once we've finished the lesson, I'll stick the video into the OneNote as well, so you can go and rewatch it if you want to.
Oh, okay. Thank you.
You're welcome.
Is it a YouTube video?
It will be a YouTube video, yeah.
You're gonna make a channel.
No, I'm not going to make a channel. It's just for your benefit, so you guys can go back and rewatch if you miss stuff. Okay, lubricating oil, also known as mineral oil. Finally, the last one is fuel oil. So fuel oil is the fuel that things like the cruise ships that come into Hong Kong burn. So this is for engines that are really, really big. The reason they burn fuel oil is because they don't need a lot of power, because there's not a lot of energy given off by fuel oil. Because the engines are enormous, they get the power that way just by size alone. It's a very dirty fuel, so if you ever see the cruise ships giving off black smoke, that's because they're burning fuel oil. It doesn't burn very cleanly at all. And it's long carbon chains, so lots of carbon in it, so it's a very dense oil and has a very high boiling point. Okay, the last one, my favorite one. The last one is the stuff that doesn't evaporate. So any of the fuel, after we've heated it to 370 degrees and it doesn't turn into a gas at all, it will remain coming off down here as a thick liquid. It does not boil, and it's called bitumen. This is how this is pronounced, bitumen.
Bitch.
Yeah, it's a great name, right? Bitumen.
Oh my god.
Very, very long carbon chains here, guys, okay? 70 carbons plus. And it basically...
Useless, right?
Sorry, Gabriel, say that again?
I can't remember. Did you mention about its uses?
Yes, bitumen is used to make tarmac on roads. So the top layer of a road surface, the black stuff, this is called tarmac, and it's made from bitumen. So we make roads out of this, basically. It's one of the main uses.
Well, there are lots of things we could make roads with, right?
Well, roads have many layers. They're quite complicated.
Like Mr. Williams.
Yeah.
Like there's like like we walked in the road on the road, right? So like this is some black thing.
Yeah.
It's a bitumen.
Yes. So basically, the very top layer of a road is made of very small stones, and then sticking it together, there's like a black liquid that's really sticky.
It's like a gum thing.
Yeah, like gum. Yeah, basically, that's bitumen.
Okay.
That's made from. It's not exactly. It's a refined version of this chemical, but they take what's left from fractional distillation and they make that sticky black substance out of it.
Oh, okay.
If you've ever got it on your hands, you can tell it just doesn't come off. It's so sticky and hard to get rid of. It's horrible.
Well, what do we do?
You'd have to use loads and loads of detergent, like washing liquid, to try and get rid of it. But even then, it would just take. You'd have to scrub it off. You'd probably.
Oh yeah, is it because detergent could dissolve oil?
Yes, exactly. Detergent is very good at breaking down fats and lipids and oil, and so this is all made from oil, of course. Okay, we're going to move on. You guys got any more questions about how a column works?
No.
No. Okay, nice. So, how do they differ? So if we look at some of these molecules, these hydrocarbons, what we really should know is that the biggest thing that changes between them is just the number of carbons. So this one's 2, this one's got 4 carbons, right? The longer the carbon chains affects a few of their properties. They affect the boiling point, and it also affects what we call the ignition point, which is how easy it is to set them on fire. And finally, it affects the viscosity, which is a great word.
Viscosity.
Viscosity, yes. Which basically means how runny they are, if that makes sense. So honey is more viscous
Than water.
than water, exactly. Yeah? And tar is more viscous than honey.
What's a tar?
Tar, it's a very good question. Tar is kind of a general name given to a chemical that's found from millions of years ago, a bit like crude oil, but it's actually found. You get tar pits in America, and they're basically like a really thick liquid which animals died and got trapped in, and then it fossilized them basically. Google it, Josiah, if you're not sure.
Okay.
Tar is also used to describe the chemical that's in cigarettes, that's like black and thick and brown. You know, that horrible brown stuff? That's tar, isn't it?
I thought that was.
Yeah, so people who smoke cigarettes, the brown colour that stains their skin and makes it gross and gives you and kills you is called tar as well.
What if they eat it? Like, accidentally?
Whoever that is, I can't hear you. You're too far from your mic.
Yeah, like, what if they eat it? Like, they suck it in.
If they suck it in, then basically it goes inside their lungs and sticks on the inside of their lungs. It's
It
not...
would be pretty hard to breathe, right?
Yeah, it just basically makes it much more difficult for oxygen to move from your lungs into your blood because there's a layer of tar in between where normally there isn't one. Okay, moving on. So, molecules in crude oil go from 1 to just over 50. There's actually a lot more than that. They can go up to 100, 150 length. So, generally, longer hydrocarbons have a higher boiling point. So, C50 will be a much higher boiling point than C10. And this is all to do with intermolecular forces, but you guys don't need to know about this. It's fine. So, let's just...
Intermolecular forces. That
Yes.
sounds like a movie.
It's A-level chemistry. Basically, what it means is, if you took two molecules with carbon chains like this, let's take like this, and they were surrounded by the hydrogens like this, and then you put another molecule next to it, exactly the same, with carbons and hydrogens, yeah? I'm not going to draw all the hydrogens because it will take too long. These molecules are slightly attracted to each other. So there is kind of an attraction force between the hydrogens and the carbons here, going across like this.
Oh, so it's like the Tesla.
Tesla?
Yeah, for physics. With this attraction.
Yes.
Electricity.
Yes, so they attract each other. So this is called an inter because it's between, right? Intermolecular, which because they're molecules, force. Okay, which is A-level chemistry if you're interested. Think of the word.
That sounds cool.
Think of the word international. What's it mean?
Like global.
No. Inter between means
Within.
It's
between, not within, between. And then national,
countries.
yeah, nations, right? So international means between nations. So if you fly internationally, you're flying between nations, doesn't it? If you're looking at intermolecular, it means between
Molecular.
molecules. Yeah,
Oh,
intermolecular. Between molecules. So in this case, these are forces that are between the molecules, okay? And so the more carbons you have in a chain, the stronger these forces are, which means if you want to pull these molecules apart, you have to put...
You need more energy.
You need more energy. Nice, Gabriel, yes. And if you need more energy, you normally use heat, and therefore they have a higher boiling point.
okay.
Here you go, I'll show it to you so you can see what I'm talking about. So, let's look. Here is exactly what I've just drawn. These two atoms are attracted to each other with an intermolecular force.
This yesterday.
You saw this yesterday? To break these intermolecular forces takes energy because we have to put heat energy in to literally pull them apart from each other. And so longer carbon chains have more intermolecular forces, which means that you need to put more heat in to pull them apart. So if you look at the boiling points of our alkanes, our first homologous series, methane boils at minus 164 degrees centigrade. Propane boils at minus 42. What do you think ethane boils at?
Negative 110.
Negative 110, yeah. So you want to pick a value that's kind of halfway between the two values you get given. So in this case, somewhere halfway will be like minus minus 90, minus 100, something like that. And then if you look at hexane, it boils at 69 degrees. So hexane will be a liquid at room temperature, whereas the first 4 chemicals will be a gas. So if we put the information in, we can see that actually these are the boiling points. You quite often, guys, will get asked to do this in your exam. It will give you the boiling points of 2 of the alkanes, and then it'll ask you to guess, or it won't say guess, it will say figure out the boiling point of the middle value. All you need to do to get this right is to pick the middle value. So just work out what's halfway between the 2 numbers and put that down. And the answer that they're looking for will be a range of numbers. So you'll probably be in the middle of it. It'll be fine.
Okay.
Yeah, so they'll always give you a range when they're looking for the correct mark. They won't be looking for a specific number. Question?
Yeah.
No. Okay, nice. So if we plot that data on a graph, basically what you should see is this. You get a nice straight line basically going up. Boiling points are linked to the number of carbons. So the more carbons, the higher the boiling point. Pretty straightforward. What's this? What is the order of fractions? That's boring. Let's not do that. Okay. We can do this process in the lab. Normally, guys, I would actually do fractional distillation with you when we're in school, but of course, because of the virus, we can't go in. But if we get time when we come back, I'll try and squeeze a quick practical in for you so you can see it done in person. So I won't go through this too much now, just because we'll do it together. Let's keep going. So the last thing I want to do with you guys today, and we've kind of already done it, is the uses or the fractions that we've looked at. So just in case I've missed anything, I'll go through this quickly. Most of the crude oil that we have is used for fuel, because by far, fuel is the most important thing that we get from crude oil. Your cars and lorries and the transportation network like trains and buses, they wouldn't be able to work without crude oil. And nowadays, guys, as we said last time, there's about 40 years, 20 to 40 years of estimated crude oil left for you guys in your lifespan. So at some point we will run out and there will be no more petrol or gasoline left over, which is pretty... Sorry?
Do we use what do we use to finish crude oil?
Yeah. Good luck with that one, Aidan. Right? So fuel is something that we should know by now. Basically, makes energy, and large amounts of fuel come from hydrocarbons because both carbon and hydrogen burn very easily. So they give out a large amount of energy, basically. So let's see. We've done this ourselves. Yeah, liquid petroleum gas, you might be used to seeing it like this in these red tanks. They're very, very flammable. In Hong Kong, though, we don't have the tanks because we just pump the gas through pipes underground, basically.
Oh no, I have it at my home.
You have these tanks?
Yeah.
Where do you live?
Yeah, I think in some airports they even have old men carrying these tanks around with bikes.
Yes, you do. It's very, very dangerous. It's probably not a great idea.
Do we use for cooking or?
These are very strong, these tanks, because they have pressurized gas in them. But yeah, this is the way that we can use them for camping. If you want to go camping, you can take a very small version of this. Basically, this is LPG, or liquid petroleum gas. Gasoline is the most common one, as I've already told you. It's put into your car. It's about 95% gasoline of octane. That's probably what it mostly is, which is 8 carbons long. But there are some other lengths like 7, 6, and 9 and 10 sometimes are mixed in with it as well. Naphtha is important for things like making plastics, which is a really important process. So every single plastic bag that you've ever used has probably been made from naphtha originally, or the plastics that are in your iPhones and your computers, and even in your clothing will come from naphtha, because part of your clothing is also made from man-made fibers, so that can be made from naphtha.
Sorry, can you go back to gasoline?
Sure. You don't need to write all of this down, guys. Unless you really enjoy it, you know, for some weird reason.
Oh, you memorize all the notes.
Yeah, that's good. Well, I suppose that's good practice for A-level.
It's A-level chemistry hard.
Yes.
Then I choose it.
You should choose it anyway. It's interesting.
That's highest.
Okay, naphtha. So naphtha used to make chemicals and plastics. It's also used in the pharmaceutical industry, as I said before. And we occasionally mix it, but naphtha is a very expensive fraction because we don't make very much of it, and it's really, really important. It has lots of uses. Luna, if you want to write all this stuff down, you can come back into this PowerPoint and look at it yourself, okay?
Okay.
Kerosene, which is also known as paraffin by civilized people, it's used in the aviation fuel for jet engines. Paraffin was originally used a lot in lighting. So before we had electric lights, most people had paraffin lamps in their houses, and so they'd put paraffin oil in them. It's actually not very good for you breathing in the fumes from paraffin oil when we burn it, though. It can cause cancer. And so people didn't realize they were basically filling their homes with gases that they really didn't want to be breathing in. So yeah, nowadays obviously replaced. We've got electric lighting and we don't have that problem anymore. Diesel is what you see lorries using. So the diesel oil's much longer carbon chains. You get less power from diesel, so you don't burn it doesn't burn as hot and give off as much energy as gasoline does. But something like a lorry, it doesn't need to go very fast. And so in this case, we don't need to put a very pure form of the chemical in. Diesel burns a lot dirtier, so you often see black smoke coming out the back of these big lorries and buses. And that's because it burns easily, but not as easily as gasoline. As a rule, Aiden, as we move down the list, it gets harder to set the chemicals on fire. So gases explode. They're really dangerous, right? Very, very flammable. Petrol will explode if you get the vapor, but the liquid, you have to basically turn it into a vapor to make it really explosive. Naphtha and kerosene will take heat. You'd have to heat them up slightly before they start to burn. Diesel as well, you'd have to warm it. So diesel engines basically heat the fuel before they burn it, and that makes it burn a lot easier. By the time we get down to lubricating oils and fuel oils, they're not that flammable. You'd have to get them quite hot before they would actually start burning and stuff. And the residue...
Slower.
Yeah, they're not very...
They move slower, or...
Sorry, say that again?
They move slower, so like gasoline, they're smoother, right?
Yes, it's more... it's less viscous.
Oh, okay. Oh, yeah.
Okay, lubricating oil, as I said, it's designed to lubricate the insides of engines. So anything with moving parts, if you didn't put oil in them, the metal would just grind together and it would slowly wear away. So to fix that, we fill them full of oil. So car engines are full of lubricating oil. If you look on the inside, they look a bit like this. Notice the color is brown and the oil is quite viscous now. It's getting quite thick, not very runny. Fuel oil is used in big, huge engines, so things like cruise ships, and also we make electricity from it, if we burn this. And then finally, bitumen, it's used to make candles, the resin, but it's also mostly used to make roads. That's the most common use.
I thought candles are wax.
Sorry?
I thought candles are wax.
Yeah, they're made from paraffin wax.
Oh, so it's wax.
Yep, so even your candles, they're made from crude oil.
Wait, it says waterproofing.
Yep.
So is the product called flax tape or flax seal the same thing basically?
No, flex tape and flex seal, Gabriel, will be a very different chemical. It'll be a mixture of different chemicals mixed together, right?
Okay.
Wax.
Guys, the reason it's called waterproofing here is because, this says waterproof, because it's made of oil, and oil and water don't mix together. So if you put a very thick layer of oil down, it's going to stop the water from getting through it.
Yeah, makes sense.
Yeah. Okay, that's pretty much it. Reduce friction. Oh, that's just a quiz. We don't need to do the quiz. That's boring.
We have homework today.
No homework today, guys. Right, that's it. Does anyone have any questions on what we went through today?
Did you check my homework?